This session is about the differentials. Another way of expressing a linear approximation is via differentials. And differentials, I can write for now, it will be dx and dy. They represent the change in x and y respectively to the tangent line to the function f of x at a. That means let's see how we can define, how we can analyze dx and dy. Okay, that's we call differentials. Okay, let's look at the graph. We do have a curve, the blue curve, f of x, and we have a tangent line, the pink tangent line. And the tangent line is the point of the tangency, at the moment is x. We will call later, of course, it will be given a. Okay, and this will be f of a, but x is. Okay, and we can definitely see all of the labels. Now, looking at the curve, yeah, if I would like to define the changes in y, changes in x, let's start actually with the changes in x. Changes in x, we're just going away from x, delta x unit. And we know, because we are in the calculus class, that delta x is relatively small. That means we are not far away from x. But this change from the number of units from x to x plus delta x, of course, is delta x, because we're going away delta x unit, delta x. And we will keep the same amount of change along the x-axis for the tangent line. Okay, that means we will call dx. Because everything what is related to the real curve, we will call delta y and delta x. Delta y is changes in y, delta x is changes in x. But this is related to the actual curve. Now, we can do the same thing, the rise of a run of the tangent line. That means the run, it's the dx, and rise, we can nicely see, we will call dy. It's like changing in y, like changing, like the amount of changes in the y along the y-axis and along the x. Okay, that means dy, we will call that this is dependent differential, and we will call this differential. And dx, which I didn't type, is independent differential. Okay? That means dy represents the amount of tangent line rises or falls, the changes in the linearization, the changes in the tangent line. Delta y represents the amount of the curve rises or falls when x changes by the delta x dx amount. And now let's look at this. We definitely know that the changes along the x for the curve and for the tangent are the same. That means delta x the same like dx. Now, how we can compute delta y? Okay, that means delta y will be that blue. This is delta y. Okay, that means this is the, I can project on the y. That means we need to find out this line segment, and we can say f of x at the moment. That means this point will be the value of the function for x plus delta x, because we're going away. Okay, that means this will be the top value minus the bottom, f of x plus delta x minus f of x. That's how we can compute. Like, for example, if this is 10 and let's say this is 7, the amount of units between 10 and 7, of course, is 3. How we got this? 10 minus 7. Yeah, just to have the idea, I will erase this. Okay, that means this is the formula to remember to compute delta y. Now, y prime is the slope of the tangent. We know this notation. We also know the Leibniz notation. Y prime could be, f prime could be defined as a dy dx. And normally we know this is just the notation. We don't really recognize this as a fraction. We're not really saying that dy is divided by dx, no. But in this case, we will actually look at this and define this as a differentials, which means we will look at dy and dx separately, and we know on the graph. We know where they are. And we can also think that it's like rise over run. Yeah, it's the slope, because derivative f prime represents the slope, rise over run. And we can nicely see the pink rise over run of the tangent line, of course, tangent line. But what I would like to do, I would like just to compute rise, which is dy. And I will take the derivative, okay, at that point, which this will be the derivative at a, times dx, okay, times the changes along the x-axis. Okay, that means this is the formula to compute dy, the dependent differential, dy. We can also say delta y, it's quite, I would say it's quite complicated, because we involving the delta x. And as I said, delta x is relatively small. Finding the value of the actual function for x plus delta x, it will be complicated. Yeah, because if the function is like trigonometric function or root function, like even rational function, some complicated function, even the polynomial, to evaluating for x plus delta x, it will be challenge. But looking at dy, it's just the derivative at this relatively nice point, because we can see delta x is not, I mean, dx, it is involved, but we're just multiplying. That means this quantity, it will be a derivative at the point of the tangency. That's nice and simple. And then we will take just this value and multiply by dx, which is like delta x. We will not evaluate the entire expression at the number like x plus delta x. That means dy, I can tell you, and we will try to compute, it's much easier to compute than delta y. Yeah, because delta y involves the actual function at this point. And now, what is the point later in the approximation? You may notice that delta y, this is delta y, which is related to the function quantity, dy is related to the tangent line. But when we will go extremely close here, dy, delta y dy, when I will go extremely close to the point of the tangency, they are almost the same. Delta y, it's almost the same like dy. Yeah? And when we are really close to the point P. That means if we end up using differentials to approximate some values, we will actually, this is our approximation. Instead of really taking, yeah, like to finding this, let me call blue dot, in order to finding this blue dot, which is the actual value for x plus delta x of the function, we can simply find the value on the tangent line. And we remember it's exactly the same like linearization that we did in the previous video. Okay, let's see. A few more notes. dy, of course, is dependent variable and depends on the value of x and dx. Yeah? And dx is given in this is given a specific value, okay? Independent variable. That means this will be given. We will know how many units we're going away. Okay, and this is just the equation. Okay, that means now I will have an exercise, which probably is not an exam type exercise. It's just the homework, like practicing. That means we can have a function, polynomial, third degree, x cubed plus x squared minus 2x plus 1. Okay? And then x is changing. We can see everything is happening at 2, the tangent line, but we're going away 0.05 units and 0.01. And the question is, we have to compute delta y and dy. And we remember dy is much simple. Okay, delta y. How I can compute delta y? We remember the top value, f of x plus delta x, minus the bottom value, f of x. And delta x is just 0.05. Delta x for the point B will be 0.1. Okay, that means this is f of 2, because x, as I said, this will be the a value too. and we're going away 0.05 units. Okay, that means f of 2 is simply the formula for the polynomial, and instead of x we have to put 2. Okay, that means it's not bad. I can get this 8 plus 4 minus 4 plus 1, no problem. But now I have to take the same function and substitute 2.05. And I did use the calculator. Okay, I did use, but we can see it is complicated. And then we can subtract these two values and get the difference, delta y. And that means this is the real difference in the values. Okay. Now let's look how we can compute dy. dy is just the derivative, we remember, derivative at the point 2, in this case, times how many units we're going away, 0.05, and later we will do 0.01. Okay, and derivative, that's the derivative. Instead of x, I will substitute 2. I can compute this number is 14, and 14 times 0.05, it's half, but we have to, it's not 7 because we have to move 1 decimal, 0.7. And as we notice, they are comparable, they are almost the same. That means instead of using a calculator or like having like this challenge of arithmetic, we can definitely say delta y is the same like dy. Okay, and I have the work for part B, the same thing. The value at 2, value at the 2.01, and the difference. And then derivative at 2 times 0.01, 0.14. Yeah, that's when we can see they are almost the same. But this is the point. We will try to avoid computing this because it's too much calculation. This one, it's a nice, beautiful work. Okay, that's me now. Oh, as I said, it's more complicated to compute delta y. It's useful to use differential dy. That means let's see how we can approximate. Okay, how we can approximate a value of the number using a differentials. That means, as I said, we would like to get the value of the function for this number. That means I would like to get, and let's call, because that's what I should do, this will be a, this is a, okay, a plus x, a plus delta x. Okay, that's what we will do. This blue dot, that's what we're looking for. It's the value, I can maybe write, value of the function at a plus delta x. Okay, that's, and we're looking for this value. But of course, we know that this is, this value, where is the value at a? This value, f of a. That means in order to get, that should be that value, I need to add the value of f of a. Okay, we can see f, this is f of a, one more time. And I have to add this distance. And this distance theoretically is delta y. Right? That means I can maybe write here f of a plus delta x equals to f of a. We can see, first of all, I have to reach this, and plus delta y. F of a, delta x is the same like dx, that means that's not a problem. Okay, f of a, it will be not a problem. But now, delta y. We don't really want to use delta y because it's complicated. I would like to approximate with dy. That means this will be the approximation. And of course, instead of that blue dot, I will theoretically get this one. Okay, this will be my approximation. But we can see we have a small error, but if we are extremely close to the point P, okay, the green dot will be almost, will be so close, will be almost at the value of the function, at the blue dot. Okay, that's me. But this is the way to approximate. To approximate the point, of the value of the function at the point a plus delta x, we will take the f of a value plus dy. Okay, and actually I would like to show you something. That means this is the approximation f of a, I will just repeat, plus dy. F of a, and how we can compute dy. We know that we need the derivative at a, and then we need that difference along the x. And if I will expand this even more, f of a plus f prime at a, and dx is always the difference between x and a. And do you recognize this? It's the linearization. That means differentials, which I can use the green. Yeah? It's exactly the same like from our previous class, the linearization. Yeah? It's just we can see the connection, yeah? through the labels, through the formulas. Okay, that means either way you may use the form of the differentials or you may use the linearization. But I still like you to know that differentials exist. Okay, and I think we did this question, estimate the square root of 4.05, but we did through the linearization, which is almost the same. Now we will use the differentials. Function, of course, is square root of x, and the nice point, we remember the nice point that goes well with the square root function, and it's close to the 4.05, it is 4. And we're going away 0.05 units. That's our delta x. And this is the approximation. That's the differentials. That's how we will approximate. I think I should type approximation. That means this is 4.05, f of 4, and this will be derivative at 4 times 0.05. Okay, derivative at 4 and the 0.05. This is 2, this is 1/4, and 1/4 times 1 over 200, right? It will be 800. Yeah, we can definitely, or I can do the different way. I can say 500. Oh, that's easier. I'm trying to get the number without the calculator because I didn't use the calculator. 500 divided by 4, 125. That's much better calculation. And then 2. Okay, that means that's the approximation. And one more time, I can write the linearization, which we will approximate the function, of course. That's actually what we're doing. It was f of a, we can see the connection, plus derivative at a, that's what we have, and times the delta x, but we will write it this way because that's the difference, how many units away we're going from x. Okay. Oh, I typed this. Okay, that's end of this session. Yeah, please just make sure that you also know the differentials along with the linearization. Thank you.